Welcome to all. Today we can discuss eccentrically loaded welded joints. We can do some problems regarding this topic. First problem. A bracket carrying a load of 15 kilonewton is to be welded as shown in figure. Find the size of the weld required if the allowable shear stress is not to exceed 80 megapascal, and the welding arrangement is given in this particular figure. Here double parallel fillet weld is there, and an eccentric load having magnitude 15 kilonewton is at a distance of 125 units away from the center of gravity of this double parallel fillet weld, and this thickness of the plate is equal to 80 units. We can treat all dimensions are in mm. Then this distance is equal to 125 mm, this distance is equal to 80 mm, and the applied load in this eccentrically loaded welded joint, that eccentric load is equal to 15 kilonewton. Here the weld length is equal to 50 mm. Here given P is equal to 15 kilonewton, that means 15 into 10 raised to 3 Newton. Tau is equal to 80 megapascal, that's equal to 80 Newton per mm square. Here B means width of the plate is equal to 80 mm. L is equal to weld length is equal to 50 mm, and that eccentricity is equal to 125 mm. Then S is equal to size of the weld in mm, and T is equal to throat thickness. Then throat area is equal to 2 into T into L. 2 into T means throat thickness into length of the weld. Here it is a double parallel fillet weld, so we can use this 2 here. Otherwise for a single transverse weld we can use that welded area is T in welded area as T into L. For double parallel fillet weld we can use 2 into T into L, and the T is equal to 0.707 S, where S is the size of the weld in mm and L is the length. Then this particular area is equal to 70.7 S mm square, 70.7 S mm square. Then direct or primary shear stress is equal to P by A. Here the given P is equal to 15 into 10 raised to 3 divided by area is equal to 70.7 S, that's equal to 212 by S Newton per mm square. This is the direct shear stress. Then from the data book, KM data book, page number 96, table 6.7, we can find out the polar moment of inertia of the throat area of the weld about G. Here in that data book on page 96 there is a table which is listing polar moments of inertia of different types of welding joints. From the table, for a double parallel fillet weld, that J is equal to T into L into 3B square plus L square divided by 6. Then that's equal to, we can substitute that value of T is equal to 0.707 S into 50 that L is equal to 50 into 3B square plus 50 square divided by 6 mm raised to 4, and that value is equal to 127,850 S mm raised to 4. Then from this figure we can find out the coordinates of the center of gravity of the welding area. Then we find that AB is equal to 40 mm. Here AB is equal to 40 mm. That means this particular height, the y coordinate, when we can treat this point as 0, then the y coordinate of this particular G is equal to 80 by 2, that is equal to 40 mm, or AB is equal to 40 mm, and this BG is equal to R1, and that R1 is equal to 25 mm. Here we can see this particular fillet weld is symmetric about both x and y axis. Then this center of gravity is at a distance of 25 mm away from this particular point, or this particular edge, or the, 25 mm away from this particular edge. That means at the middle of this span length 50 mm. X coordinate is equal to 25 and y coordinate is equal to 40. Then BG is equal to R1, and that's equal to 25 mm. Then maximum radius of the weld is equal to R2. This maximum radius, this particular length is equal to R2, and that R2 is equal to root of GB square plus AB square, and that's equal to 47 mm. Then shear stress due to turning moment, or secondary shear stress, is equal to, we have already derived this particular equation. This equation, tau 2 is equal to P into E into R2 divided by J. That's equal to P is equal to 15 into 10 raised to 3, E is equal to 125 mm, and R2 is equal to, already found out in this particular step, then 47. That's equal to 127,850 S is the polar moment of inertia. That's equal to 689.3 by S Newton per mm square. We have found out the secondary shear stress as 689.3 by S Newton per mm square. From this triangle, if this angle is equal to theta, we can easily find out this angle means angle between this GB and AG is equal to theta, and that from that right angle triangle GBA, cos theta is equal to R1 by R2, and that is equal to 25 by 47. This 25 divided by this 47, that's equal to 0.532. Okay, then we know that the resultant of shear stress is equal to resultant of this tau 2 and tau 1, and the angle between those two shear forces is equal to theta. Then the resultant of this tau 2 and tau 1 is equal to root of tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. We have already have this equation, the resultant of two forces when the angle between their lines of action at the meeting point of the line of action of those two forces is equal to theta, then the resultant is equal to this one. Then we can find out this tau as 822 by S, and that must be equal to given shear stress, maximum permissible shear stress is equal to 80. Then we can equate this 822 by S. We can equate 822 by S to 80. Then we can easily find out this S, the size of the weld, as 10.3 mm. Here 80 mm means the allowable shear stress is not exceed 80 megapascal. From this given data, we can equate this particular shear stress. The resultant shear stress must be equal to 80. Then S is equal to 822 by 80, that's equal to 10.3 mm. Okay, this is the answer for the first problem. And there is another problem. A rectangular steel plate is welded as a cantilever to a vertical column and supports a single concentrated load P as shown in figure. Determine the weld size if the shear stress in the same not exceed 140 megapascal. Here the difference between the question 1 and question 2 is that there is another additional longitudinal weld is there, which is parallel to the line of action of the external force. Then there is a transverse weld and also double parallel fillet weld. That is the difference. Here, first we must calculate the center of gravity of this center of gravity of the weld system as shown in figure, or the coordinates of G. From the KM data book, page number 96, table 6.7, there is an equation for this x coordinate. There is an equation which represents the value of x. That x is equal to L square divided by 2L plus B. We know that this particular welded portion is symmetric about x-axis, so that the y coordinate of this particular G is equal to 0. If we treat this as this center line as x-axis, if we can treat this as x-axis, then that y coordinate of center of gravity already found out, or already known, that is equal to 0. Y coordinate 0. X coordinate we can easily calculate by using this equation, which is given in the KM data book, page number 96, table 6.7. Then x is equal to 12.5 mm. Then again from the same data book we can find out the polar moment of inertia of the throat area of the weld system. J is equal to by using this particular equation. This equation also given in the KM data book, page number 96. And that J is equal to 275 into 10 raised to 3 S mm raised to 4. Okay. Then the distance of load from the center of gravity, distance of load from the center of gravity, this E is equal to this 150 plus this 50 minus x. If this distance is equal to x, then this E is equal to 150 plus 50 minus x is equal to, that's equal to 187.5 mm. And R1 is equal to R1. This distance is equal to 50 minus x. R1 is equal to 50 minus x. That's equal to 50 minus 12.5. 50 minus 12.5. That's equal to 37.5. Then we know that the maximum radius of the weld R2. We must calculate this maximum radius R2, and that R2 is equal to AB square plus GB square. That's equal to 62.5 mm. And cos theta is equal to R1 by R2. We have already discussed this calculation procedure for this calculation. Then cos theta is equal to 0.6. Then we know that the throat area is equal to 2 into 0.707 S into L plus 0.707 S into B. That means 2 into 0.707 S means that is the area of the double parallel fillet weld. That's equal to 2 into 0.707 S into L. L is the length of the parallel fillet weld, plus this particular value 0.707 S into B. B means this distance. That means this is the area of the throat area of the transverse fillet weld. That's equal to this one. Transverse fillet weld from this point to this point. Transverse fillet weld, and that length is equal to 100 mm. Then we can find out the total area as 141.4 S mm raised to 2. Okay, then direct or primary shear stress tau 1 is equal to B by A. We have already have this value of P, 60 into 10 raised to 3. Then divide by A, that's equal to 424 by S Newton per mm square. Then shear stress due to the turning moment or secondary shear stress is equal to P into E into R2 by J. We have already found out the values of this each terms, then we can substitute that values here. Then tau 2 is equal to 2557 divided by S Newton per mm square. Then the resultant by using the same procedure as in the case of the first question, tau is equal to root of tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. By substituting all the values in this particular equation, we can find out that tau as 2832 divided by S. This is the resultant shear stress, and that must be equal to maximum permissible shear stress 140 megapascal. By equating these two values, we can easily find out the value of S, size of the weld. That size of the weld is equal to 2832 divided by 140, that is equal to 20.23 mm. 20.23 mm, the size of the weld. That is the final answer. That is the final answer. Thank you. Thank you all.